Okay, now to the beginning of the line, right? So let's look at the generator, and when I apply a certain voltage waveform, does actually all of the voltage uh, appear on the transmission line or not, right? So in this case, I can say that there is a source voltage Vs, which is a function of time. There is a source resistance Rs and a current Is on the left hand side this time, right? So the transmission line starts from the first inductor capacitor, right? So on the left, what do we have? We have Vs minus, let's call this potential as V, okay, Vs minus V divided by Rs is equal to Is, okay. And on the right hand side, we have V equals V plus. So remember, there is no voltage in the reverse direction. This is where all voltages are beginning, right? Assuming that the transmission line goes forever on the right hand side, that whatever voltage that you launched on the transmission line is just going off to infinity, right? So we are not worried about any voltages coming in the backward direction right now, right? We are just launching the voltage at the input side. So we only have the V plus, right, which is the t minus x by v function, right? The function that has t minus x by v as the argument. That's the only function that is required to describe the voltage on the transmission line at the beginning of the line. Okay, so I is this V plus by Z naught. Okay, so the voltage and current in the transmission line in terms of V plus and V minus, right? So the onward going voltages, right? And then on the left hand side, we have simple Ohm's law for the source resistance. So remember that Is and I going into the transmission line are the same, right? So we can say that Vs minus V, but V is V plus, right, by Rs is equal to V plus by Z naught. So here the unknown is V plus, right? So we want to find V plus given your Vs, right? So a simple rearrangement will give you Vs times okay. So we are seeing something very interesting here, right? That is, if I have a source resistance Rs and if I have a source voltage Vs, the entire amplitude Vs does not actually get launched on the transmission line, right? But only a fraction, and the fraction is Z0 by Z0 plus Rs. Okay, so if Rs were equal to Z0, then we essentially see that V plus is Vs by 2, right. So, only half the voltage goes onto the transmission line. Okay. So, now I think we are ready for a concept in transmission lines which we call as lattice diagrams, right. So, essentially let us try to picture what is going on when I have a source voltage, sinusoidally changing source voltage that is connected via a transmission line to a load ZL or RL, right. Let us just keep it simple and just consider a simple resistive load for now, right. So, let us try to verbalize what the mathematics has told us so far, right. That we notice that whatever be the voltage, right, at some particular time t, right, Vs is a time dependent function based on the value of Rs, the source resistance, and the impedance, the characteristic impedance of the transmission line. We have a portion of the source voltage Vs that gets launched on the transmission line, right. So, from the previous slide we can say Ts is Z naught by Rs plus Z naught, right. So, a portion of this voltage gets launched on the transmission line and it slowly moves. So, this axis is x and this axis is in time, right. So, for future times, right, we are noticing that the voltage is essentially traveling to different points along the transmission line, right. So, this is the lattice diagram or the echo diagram, right. So, the reason why we call this echo diagram is quite natural, hopefully. It is almost like these voltages, right, are sort of bouncing back and forth between the load and the source, right, trying to establish some kind of a steady state. Okay. So, we are noticing that the voltage slowly moves to the right, right, and it takes certain delays, right. So, if I were to look at some particular point in the middle of the transmission line B, I will notice that it takes time tau 1 to reach there, right. So, let us assume for simplicity that this Vs is just a pulse, right, is a short pulse of say 1 volt, right, and I am launching this 1 volt at time t equals 0. This 1 volt, not all of it first enters the transmission line, right, a ratio of 1 volt times Z naught by Rs plus Z naught moves, right. So, let us say that Rs is equal to Z naught. So, we have a half a volt voltage that is appearing consecutively at locations in positive x direction at future times, right. Slowly that plus 0.5 volts is appearing at all points along the transmission line, and the time of arrival of this 0.5 volts at B, right, is tau 1, right, and then it takes a further time tau 2 to get all the way to the load, right, and once it reaches the load, what happens? There is some amount that gets reflected, right. So, let us assume that RL is not Z naught, right, the load resistance is not Z naught, because if it were, then the reflection is 0, right, then we do not have any bouncing at all. So, there is essentially the voltage just appears, that half a volt just appears at the load RL, right? But assuming that if RL was different from Z0, then I expect some small fraction to be launched backwards on the transmission line, going in the opposite direction or minus x direction, and the fraction of it that is going backwards, right, is the product Ts times gamma L, right, where gamma was RL minus Z0 by RL plus Z0, right, and then it takes tau 1 plus tau 2 to come back to the origin, and when it comes to the origin, it sees the resistance Rs, right, and again you can think of that Rs appearing like a load at the end of the transmission line, and there would be further reflection at the source, right, and now you can see that these values for Ts and gamma L are all less than 1, right. So, you can convince yourself that regardless of whatever RL and RS you have in comparison to Z0, the values for gamma and T are all the modulus of gamma and T are less than 1, right. So, as I keep multiplying these numbers together, I will actually get smaller and smaller values, right. So, it's sort of the voltage went to the load, came back, and it's sort of bouncing back and forth, and each time as it goes to the ends and comes back, the magnitude of this voltage diminishes, right. So, this is in fact, in reality, this is exactly how we see voltages permeating in circuits, right. Now, the reason why we did not care about it for slowly time varying circuits was this entire infinite bounces, right, happens in very short time, right. So, when the distance between A and C is relatively short, right, or another way to put it, the time it takes for the signal to go from A to C, right, say that time is much shorter than the speed with which, or the rate at which, the voltage of the source is changing, right, then you will almost see a steady state behavior, right, that yeah, the speed of light delay, right, and the associated effects do not sort of muddy the voltage and currents that we see at different points. But if we have a sufficiently long transmission line, where the speed of light delay now through this transmission line is much longer than the period or the rate of change of the source voltage or current, then we see this kind of a echo diagram, right, where the voltage and current are bouncing back and forth. Now, it seems very odd to use the sentences the voltage is bouncing back and forth or the current is bouncing back and forth, right. Remember that voltages and currents are not physical entities like a ball or some kind of a javelin stick or something like that, that I can throw and it goes and comes back, or a boomerang, right. But remember that when I say that something is moving or rattling back and forth, it is the appearance of movement, right, that what voltage was measured at one particular location, say A, again seems to be measurable at B sometime later, right. So, it seems like the voltage has moved from A to B, right, but it is more like the voltage has appeared at B sometime later, right. So, this retardation effect or the time delay effect is how we have successfully modeled using this LC ladder, right, and hopefully I will try to bring in more new videos with the same Shive wave generator to try and understand this concepts of reflection and transmission. Okay. All right. So, we will end the lecture here and we will continue in the next class.